In this question, we're given a hypothetical chemical reaction. AB yields C plus D. A plus B yields C plus D. And we're given this energy diagram, which is sometimes referred to as a reaction coordinate diagram. And these are very important in things like organic chemistry and for many other types of reactions. They allow us to know something about the energy of what's going on. So being able to interpret this is a valuable skill to have. The first thing it says is, what is the heat of the reaction? Well, here we want to look at the overall energy. So the overall energy of A plus B is here. The overall energy of C plus D is here. So we went from 200 kilojoules per mole down to 100 kilojoules per mole. Said another way, 100 kilojoules per mole of energy was released when this reaction occurred. So the heat of the reaction is minus 100 kilojoules per mole because 100 kilojoules per mole of energy was released. Now we're at lower energy because of the law of conservation of energy. To go from a higher energy to a lower energy, that energy must be released, and we lost 100 kilojoules per mole of energy. Since this is essentially lower on the energy diagram and this is essentially higher on the energy diagram, this reaction has to be exothermic. We started at a higher energy, we went to a lower energy. In order for that to happen, again, because of the law of conservation of energy, this energy must be released. Any reaction where energy is released is exothermic. Another way you could do this is you just figured out the heat of the reaction is negative. If the heat of the reaction is negative, it's exothermic. It's another way of saying the same thing. Next, it says, can you determine the activation energy? Yes. Okay, reaction coordinate diagrams like this one allow us to determine the activation energy. The activation energy is the difference in energy from A and B to the transition state up here at the highest point of the peak. So this is 200 kilojoules per mole, and this is 400 kilojoules per mole, which means we have to add the difference between these, which is 200 kilojoules per mole. This is the activation energy. So to review, the activation energy is the energy difference between A and B and the highest peak, which is at the transition state of this reaction. So this is the activation energy here. So yes, we can determine it, and it is 200 kilojoules per mole, the difference between those two values. Can you determine the activation energy of the reverse reaction? Sure you can. You can determine the activation energy of the reverse reaction if we go in this way. But in this case, the reverse reaction is going to have a higher activation energy because we're starting at 100 kilojoules per mole if we want to go backwards, and we want to get back over here, and we still need to go up to 400 kilojoules per mole. So we still need to increase all the way up to the top of this peak at the transition state. So in this case, the distance between here, I'm going to put it over here. The distance, I'm going to put it here, I guess. The distance between here and here is 300 kilojoules per mole. It's a more of a difference. Said another way, this is a higher peak if you're going in the reverse direction than if you're going in the forward direction. So here, yes, you can determine the activation energy of the reverse reaction, and that activation energy is 300 kilojoules per mole. So again, interpreting these reaction coordinate diagrams, or they call them energy diagrams, is very, very important for many forms of chemistry where we study chemical reactions.